Welcome to this how-to recording for Flashy Science virtual experiments. Now you may have already seen some of the quick video guides that we do that are just a few minutes long and give you the essentials of any of the virtual experiments that we offer. This is going to be longer though, because we're going to use one of the virtual experiments to explore an actual experiment, do it in its full sense, obtain data and perform analysis. And we're going to use the gas laws virtual experiment and perform an experiment of isothermal ideal gas conditions, so that is constant temperature. Now the gas laws experiment is one that is for members only, so I've logged in to the website. So if you want to use this experiment, you'll need to subscribe to us. But here's the home page. You can scroll down and see all of the experiments that are available. I'm going to click on the gas laws to go to the gas laws section. Now, as with all our experiments, there are a number of tabs that show you the real world relevance of the experiment that we're going to do. So where in the world gas laws and thermodynamics are important. A number of tabs show a variety of ways of obtaining instructions, either a simple A4 quick guide, full written instructions in a document, and then at the end here there's a link to our YouTube video of the quick video guide. There are then there's a document that gives the full scientific background to what's going on here, and a whole load of questions and things to try out. Some of them are much more straightforward than others, so whether you're a student or a teacher, hopefully this will give you inspiration for how to use these virtual experiments. But let's go to the experiment itself. So we click the Go button, we go into the lab, and we'll soon see the gas laws experimental equipment. Now in the center of this there is a cylinder, and of course this is where the gas will go. So we'll fill that with gas, and we do that with the gas select unit. So click this button to turn it on, and then click and drag this dial to the gas that we wish to choose from these four available. I'm going to stay with argon gas, and then click the add vent button, and you'll see that the gas goes into the cylinder. Now really argon isn't yellow, that's false colouring just to help, but the piston inside the cylinder rises, and also you may have noticed that this indicator on this temperature dial moved to show a certain temperature here. So we can measure the temperature using either the black scale in Kelvin or the red scale in degrees centigrade. We'll come back to this later. So the cylinder has this piston, as we've mentioned. There's a height scale. This is in centimeters. The internal diameter of the cylinder is 5 centimeters. And later we'll see how we can use that to calculate the volume of the gas. The height will change. The height of the piston will change, and we'll measure that, but of course the internal diameter remains constant, and so the internal cross-sectional area is always constant. So volume is one thing we can measure. This unit here, the force control unit, allows us to vary the pressure. Now the pressure applied to the gas at the moment you may think is 0, but that isn't correct. The additional force applied to the piston is 0, but remember there is always atmospheric pressure. So the gas is under atmospheric pressure at the moment. The force control unit adds additional force so that additional pressure can be applied to the gas. And this again we'll come back to in a moment. So first of all, let's look at changing the way that we control the temperature. I mentioned already that we're going to be looking at constant temperature. Now at the moment there's a blue jacket around the cylinder, and this is an insulation jacket. So it protects the cylinder thermally from the rest of the universe. Now that means if we apply pressure, if we add force, the temperature we'd expect that to rise. The temperature of the gas should rise. That isn't what we want for this particular gas law that we're exploring. We want temperature to not change. And we can do that using the thermal control unit here. So if we click on this dial, it will change it from position 1 to position 2, and now the jacket has turned red, and that means it's now a thermal control jacket. A screen has lit up, and we can control the temperature, set the temperature by clicking and dragging this dial, so anywhere between 0 and 100. 0 and 100 just mean minimum and maximum in this case. Once we're happy with the dial position, click set, the temperature changes. In this case it's increased, and you may have noticed that the position of the piston also changed. So the height increased. Well, that's what we'd expect, of course. If you increase the temperature of a gas, you expect it to expand. Well, this can be the temperature of our experiment now. So we'll fix this, and if we change the pressure now, we should see later that the temperature doesn't change. So we need to record some of these values. Now, really encourage you to use pencil or pen and paper. Use a lab book and draw plots by hand. Because this is a recording, I'm going to use a spreadsheet so that you can see the processes that go on. Now, I'm using Microsoft Excel, but you can use spreadsheets that are available and are freely downloadable. Any of those, I'm sure, will do an adequate job here. But in the spreadsheet, if you're using that, or in your lab book, if you're using one of those, writing by hand, you need to record the conditions. So I'm going to put in temperature equals, and if we go back, we can measure the temperature. I'm going to measure this in Kelvin, and it's 700 here, and it's about 730 Kelvin. So I'll put that into the next cell and then put K for units. Remember to include your units always. Right, so we're up and running. Now, I mentioned already that there's a fixed internal diameter. So let's put the diameter of the cylinder in, because we will need that for calculating the pressure and the volume. If you remember, the diameter is 5 centimeters. Sorry, I should put these in separate cells, like this, 5 centimeters. And it's important to put those in separate cells actually, so that the 5 is a number in the spreadsheet. Now, if you don't know how to use equations in spreadsheets, I'll show you now. It's very simple. So we're going to calculate the area from the diameter. So area equals, this is just text, it's not part of the equation. Now, generally, in most spreadsheets, to perform a calculation, rather than putting numbers in, so if I put 5 plus 5, it just holds that as text. It's not doing the calculation. Delete that. If I do equals first, everything else that follows is a calculation. So if I do 5 plus 5, the answer is 10. That's nothing to do with the area. I'm just giving that by way of example. Now, area is related to diameter, of course, by pi times the diameter squared divided by 4. And I'm going to convert the area into meters squared rather than centimeters squared as well. So first of all, put an equal sign in, and then in this version of a spreadsheet, type in pi, open brackets, close brackets, for the number pi, and then we're going to multiply that. Now remember, it's multiply it by the diameter squared and then divided by 4. So I'm going to open two lots of brackets, click the cell that the diameter is on, and it appears in the equation. Now I'm going to convert this to meters from centimeters, so divide it by 100, so we're in meters. Close the first set of brackets, square it, close the second set of brackets and divide by 4. So you can look at this equation and see that we have pi times the diameter in meters squared, so usually this caret symbol, it gives you the power of, and then divided by this slash 4, and that will give us the area in meters squared. Now, to make it easier, although we can refer to this cell as B3, in this version of a spreadsheet, we can click here where it shows B3 and type in the name that we wish it to have. So we'll call it area. Right, so we can go back to the experiment now. Now I mentioned already how the force control unit adds force and changes the pressure, but actually we can take a data point already. We can take one now, and that's because we are applying pressure. There's atmospheric pressure, and the atmospheric pressure results, with this temperature and the amount of gas that we have, results in a piston height shown here. So let's get ready to start taking the data straight away then. So back to the spreadsheet. We need to know what atmospheric pressure is. That's an important part of the calculation. So atmospheric pressure equals, well, if we just take the standard pressure, standard atmospheric pressure is 10 to the power 5 pascals. Now, if you're doing this on paper, you can write 10 to the 5 pascals. For a spreadsheet, it's usually 1 E5 means the same thing. The E means times 10 to the power 5. And put in the units. And I'm going to change the name of this cell again so that it's easier to use. I'm just going to call that Atmos. There we are. Now we'll set up some columns. So in your lab book you could draw a table, and this should hold what we are going to measure and what we're going to plot. So we're going to measure the force that we apply, force in newtons, and then we're going to calculate from that pressure in pascals. There we are. So we've got these two shown here. We're also going to measure the height of the piston, so height in centimeters, and from that calculate the volume of the gas in meters cubed. So just change the width of the column so that we can see everything there. Now the first data point, the additional force, is 0, because remember the force control unit is off. So the pressure is just the atmospheric pressure. So what we're going to do is here create an equation. So atmospheric pressure, so that's this one. I can click on it to introduce it, and it shows itself as Atmos because that's what we called the cell, remember. And then we're going to add the additional pressure, which is 0 in this case, but we'll do the calculation. And the additional pressure, remember force is related to pressure as force divided by area. So it's the force, so click on this cell, E2, divided by the area. So click on the area, you can see that's now in the equation, close the brackets, and there we have the pressure. Now I'm just going to change the format of this so that it shows as a scientific value with an exponent. There we are. So that means 10 to the 5. So let's measure the height now. So here we are, the piston's up here. So we've got 5, 10, 15 centimeters. Now the accuracy with which we can measure this is limited. We do that deliberately because we then have to take multiple data points. So I'm going to call this 16 centimeters. There's uncertainty associated with that measurement, but that's always the case no matter what measurement is made. Now actually it's 16.0 centimeters here, so I think we can see half centimeter jumps with this. So I'm just going to change the format of this so that we can see 1 decimal place as well. There we are. Now if you're writing this in your lab book, you can add the 0 as a matter of course. If you're using a spreadsheet, you change the format of the cells. So now we calculate the volume. So calculation on the spreadsheet, we press equals, and the volume is height times area. But the height is in centimeters, whereas we want volume in meters cubed. So we'll put the height in, but convert it into meters, so divide it by 100, and then multiply that by the area of the piston, and then we have the volume. Now I'm going to convert this as well, the format of it. I was using a quick key before, but if I do format cells, and then go down to scientific. 2 decimal places is fine. There we are. We have that in a more scientific format now. Right, so now we're ready to take more data. So we'll go back to the experiment. So we're going to apply force to this. So turn on the force control unit with this button here. The light comes on here and the display lights up. Now there's 2 numbers here. We've got the first one is the step. This is the amount by which the force changes each time we click an up or a down arrow here. The second number is the overall amount of force that is applied. Of course, we haven't done anything yet, so that's 0. Now the keypad is used to change the step size of force. So click the set button and that top number will start flashing. Now you can edit that number. So if I just put in 100 to make 100 newtons and then press set again. There we are. Now we can increase the force applied. No changes have yet been made, but if I click the up arrow, look, the total force has changed to 100 newtons, but did you notice the piston drop in height? So let's look at the data we have here now. Force 100 newtons and the piston height, I'm going to call that 10 centimeters. Clearly it's a little bit more, but I can't measure that precisely. So 100 newtons, height 10 centimeters. And we can now do that again. So increase the height, increase the force, that reduces the height. So we've now got 200 newtons and a height of 8 centimeters. 208. And do that again. 300 newtons, 6 centimeters. Do it again. 400. Okay, I'm going to call that 5 centimeters. And the final data point that I'll take for this is here. So 500 newtons, and we'll call that 4.5 centimeters. Sorry, that was very quick there. I'll go back to the experiment. 1, 2, 3, 4, and about halfway between 4 and 5. So we'll call that 4.5 centimeters. Now we could increase the force further, as you can see, and we can reduce it again, but just for the purposes of this recording, I'm going to leave the data as that. Now, if you're doing this on paper, you then need to do lots of calculations. So for each of these forces, calculate the pressure, and for each of these heights, calculate the gas volume. Now, being a spreadsheet, we can do this quickly. If we click on a cell that has the equation, we can then click and drag the bottom right corner, and that will fill all of the cells with the equation, but moving on the data that are referred to by their coordinates. So we've got the pressure here, this final one, look, it has E7 in it because the number has been moved on 1 each time we drag down a cell. We can do it even quicker if we just highlight the cell and double click the bottom right corner and autofill down there. So now we have, look, this is great, pressure and volume. Fantastic, what a wonderful set of data. Now you may think, well, let's plot our data. Well, indeed, let's try that. So I'm going to highlight the pressure and volume, and I'm going to create a plot. Now you might like to do this by hand. Really recommend you do it by hand, but for the purposes of the recording again, that's going to not be possible. So I'm going to insert a chart in Excel. Now Excel, I have to say, isn't great for creating plots, but if you use a scatter plot and just with the data points marked scatter, and we'll get rid of this unhelpful title and this unnecessary legend, and we now have a plot that shows pressure and volume. Now we need to add axis titles, but actually I'm not going to do that here. I'm going to delete this plot in a moment. Now I'll explain why. For constant temperature, go and look at the instructions and the background information on this, but for constant temperature we expect pressure and volume to be inversely related. Pressure is proportional to 1 over volume. And that comes from the ideal gas law equation, obviously. PV equals nRT, where N is the number of moles, R is the universal gas constant, and T is temperature, of course. So if temperature doesn't change, only P and V change in the equation. Now, if we look at the data we plotted here, does this show that pressure is equal to 1 over volume? Well, it's consistent with it, but we're not showing that directly. So it's far easier to create a straight line plot. And to do that, well, what should be a straight line plot, to do that, we need to invert one of the data sets. So I'm going to delete this plot now and go back to the data, and I'm going to invert the volume. So here I have 1 over, I'm just going to call it vol, and the units now are in per meter cubed, or meters to the -3. Again, you can calculate this very easily and put it into your paper lab book, or in the spreadsheet we just do 1 over the cell, the volume value, and then we can double click this bottom right hand corner, autofill the rest of the column, and we now have a column of 1 over volume. So now let's look. If we highlight the pressure column and the 1 over the volume column, by the way, on the Mac I'm pressing the Command key to do that highlighting. If you're on a Windows PC, it might be the Control key, I think, but have a play, see if you can work out how to highlight the 2 columns of interest. Now I'm going to add the scatter plot with just the data points, and I'll get rid of the legend, I'll make this bigger, and I'm going to create a title that's more meaningful. So I highlight this title, and I'm going to call it Volume Pressure Plot with Constant Temperature equal to 730 Kelvin. There we are. Now we need to know what the axes are, so we're going to add axes labels. So axis titles they're called here. So the horizontal axis title is pressure. In pascals. And then we'll add a vertical axis title, which is 1 over volume. So what I'm going to do with this is start by opening brackets, 1 over volume, and the units of that are in meters to the -3. And then I'm just going to format those last 2 characters, the -3, make them superscript so that it appears nicely formatted. And I could change the format of the numbers here to remove the extra decimal points here, remove a decimal point from this one. I'm not going to bother doing that now. But let's look at the data. Look, we've got something that looks approximately like a linear relationship. Oh, excellent. So this means that we've seen that the constant temperature, or isothermal gas law, is right. So pressure is proportional to 1 over volume in an ideal gas where there's constant temperature. Now we can add a trend line to this, so that's a fit line. You can do this if you've plotted the graph on paper as well. You can either do it as a line with a best fit by eye, or you can use a least squares fit calculation. Now that's essentially what this will do. It's no different from you doing it by hand. But I'll add a trend line, I'll make it linear, and in the options I want to display the equation on the chart. Okay, the equation is here. I'm going to increase the size of that so you can see y is 1 over volume, x is the pressure, and we now have a gradient between the two. Now there's also an offset here. We'd normally, if you look at the gas law, you'd expect this to go through the origin, 0, 0. But look at the data, look. They don't fit, or they don't lie on the linear fit line. And that's perfectly normal because there's uncertainty in all data. One of the things this demonstrates with the flashy science experiments, that we incorporate this uncertainty that you see in real experiments, and that teaches you to be able to handle real data sets. But look, we've got a gradient as well. The offset 33, if you look at the values of 1 over volume, they're in thousands, so this is a very small offset really, so we can be quite confident about the goodness of fit here. We could also include the r squared value as one of the options when we included the fit, and that's a goodness of fit parameter. I'm not really worried about doing that here at the moment though. So from this gradient, what can we get from that? Well, remember PV equals nRT. The gradient is related to N, R and T. You'll have to do some maths to work out quite how it's related, but it's very straightforward. We know the temperature, the universal gas constant is constant, and so this can allow us to calculate the number of moles of gas in the cylinder. So you can see from a really quick use of the gas laws virtual experiment, we've been able to explore one of the key gas laws, the isothermal or constant temperature gas law. We've got realistic data, we've been able to plot it, do some analysis and obtain something meaningful from it. You can do this for constant volume, for constant pressure, or for adiabatic processes where pressure, volume and temperature all change. So there's all sorts of things to explore with this experiment. Let's go back to the main screen here, and really hope that you enjoy this and come to learn and understand more about how ideal gases behave.